Yes, it's going. If somebody can confirm we're live. We are. Thank you very much. So, welcome everyone to another fine seminar. I think we have today a kind of a different menu that I hope many of you will appreciate, always along the lines of social evolution, but maybe from a different angle. I am not planning on saying much right now because it is my great pleasure to have one of our young scholars, young colleagues who has been a regular participant, a regular member of the fine community, Kaya Tombak, who is a postdoctoral fellow in the Postdoctoral Society of Fellows in CUNY, New York, in the USA. Kaya is hosting our speaker today, and so that's all I will say now. Kaya, if you would be so kind to introduce our speaker, it's all yours.
Thank you. And thank you so much for coming, everybody. It is my great pleasure to introduce my friend and colleague, Dr. Joe Bak-Coleman. Joe studies collective behavior and has moved from studying this in fish to studying it in humans. He completed his bachelor's and master's at Bowling Green State University in Ohio. And then he went on to a PhD at Princeton in their Department of Ecology and Evolutionary Biology, where we met as grad students. He worked with Ian Cousin and Dan Rubenstein there. He then did a postdoc in Seattle at the Center for an Informed Public and the Data Science Institute at University of Washington, working with Kate Starbird and Jevin West. And he is now a researcher at the Columbia University School of Journalism, working with Zeynep Tufekci. Joe has, I was just talking about this with my husband, David, the other day. What is it that's so amazing about Joe? And I think we basically distilled it down to he really thinks across disciplines at a broad scale and into the future in a really unique way. And he's still very humble and great to work with. His very advanced statistics skills made him a go-to in grad school. And he took the initiative to organize weekly workshops to guide us through Richard McElrath's Statistical Rethinking book. Very generous with his time. And he has really taken off now studying political polarization of online collective behavior in humans at a time when these dynamics are really shaping our world. He had a very influential PNAS paper out in 2021 calling for more stewardship of collective behavior on a global scale. And he has just published, hot off the press, a paper in Nature proposing a new UN body for regulating information and collective behavior online. So he's going to be speaking to us more about his statistics passions today, and he has promised a very spicy talk. And with that, I give you Joe Coleman.
Right. Thank you so much, Kaya. Kaya, as always, says things that are extraordinarily kind to make you feel good about yourself. Is the right screen sharing or the wrong screen?
We see your presenter view.
All right. How about now?
There we go. Yep.
Okay, great. I can't see the chat. I think I can make myself see the chat. But so on the off chance that anyone needs to say anything in chat, you have to interrupt me, please let me know. All right. So this is a talk about social evolution, or cultural evolution, I think. And it's a talk about tool use in humans. And it's a talk about hierarchies and their impact on collective wisdom decision-making. But it's also a 120 slide opinionated talk on power analysis. And so as ecologists, you've probably gotten wind of the fact that psychology's kind of replication crisis is migrating into your field, and there's a push for more reliable research. Organizations like Sortie exist now that advocate for adopting open science principles to try to clamp down on questionable research practices and such. And things like registered reports and pre-registration are becoming more commonplace in ecology and evolution, once sort of a thing that was unique to social science and biomedicine. And this all comes out of the replication crisis, which is this concern that low rates of replication indicate large portions of the scientific literature are false. This concern kind of started in biomedicine and then migrated its way over to psychology. And the paper that you've probably read is this paper by John Ioannidis called Why Most Published Research Findings Are False. And this is a very declarative title with a very strong claim about the state of science. There's no caveats for the field or discipline. There's no caveats for anything. And this has been the kind of core background, the core theoretical model behind scientific reform. I think we need to kind of go into a little bit. So in null hypothesis significance testing, the p-values you get, you see if it's less than 0.05, there were 4 possibilities. One is you have a true positive. It's the probability that your p-value is less than 0.05, given that a thing is actually true, which is 1 minus beta, or your power. False negative, which is 1 minus your power. A false positive, which is your alpha, the rate you chose for that. And true negative. These are the only possible outcomes of a study that looks at null hypothesis significance testing. And this is a core to this theory and model. And what we really want to know is this something true? We want to know the probability that it's true, here the positive signal given this vertical line, that you observe significance, right? And importantly, these aren't the same thing. The probability that you get significance if something's true is not the same as the probability that it's true if you get significance. This is just a basic law of conditional probabilities. So some math needs to get worked out, and this is just Bayes' rule. We're not going to go too deep in the math here, but you can work this out, and what you find, you can start plugging numbers in. So if I have a 40% power and a 0.1 prior chance of the thing being true, so the thing's kind of unlikely, but after I get significance, there's a 47% chance that it's true. So even with significance, it's more likely not true than true in this framework, which is kind of the core idea underneath of this this model and this idea. And John Ioannidis extended this to think about bias towards significance. So the idea that lots of things that publish are significant. Publishing null results is harder. We've all had a null finding, and a peer reviewer says, yeah, but the results are null, so we can't learn anything. And if you kind of take this math and you plot it out, you get these little plots that say on the x-axis, the pre-study odds. So on the left half, it's something that's impossible. This is like ESP, and on the right half, it's obvious. Do apples fall? And the post-study probability is the probability after you've got significance of a thing being true. And we see that the pre-study odds are low. Even if you get significance, the probability that a study is true is low. And as we go across the colors, we see this sort of bias term. So the more biased the literature, as it goes from blue towards orange, the less likely things are true, right? So this is the core idea here. And he argued that the presence of bias in the literature, combined with this sort of basic probability theory language of how true and false positives kind of are navigated in this space, and low-powered studies on average, indicates that it is a fact that most research is false. And if you look at the distribution of z-values, this is in medicine, right? There's a conspicuous chunk missing of things that aren't published that are kind of near zero. This is pretty good evidence of bias in the literature. I don't think anyone doubts that significant findings are overrepresented. And so really this argument comes from the idea that low power and bias towards significance proves published research is false. But there was no data here, just a theoretical model, right? And there's just an assumptions going in here. And so a few years later, psychologists conducted this large replication survey of a bunch of studies, and they tried to replicate them best they could. And you probably read about this or heard about this. About a little under half of stuff replicated, most things didn't. And here the red dots are the non-replications, the green dots are the successful replications. And we see this sort of pattern where some things seem to follow the original effect size, but a lot of it falls below it, and many things aren't significant. And this was seen as evidence that this theory Ioannidis had was true. And so then to fix it, we have to think about what causes bias, right? And so the first source of bias is the file drawer problem, or tolerance for null results. This was brought up in 1979 by Robert Rosenthal. And just the idea that you could have a world where you conduct 20 studies on just noise, and 1 in 20 gets published, and then everything that's published is just false positives, right? Or you could have a world where most things are true, but you exist somewhere in there. And the more things that go unpublished because they're null, this file drawer sort of causes bias, right? The second idea is this thing of questionable research practices. So this is like p-hacking and related things. And if you take this model and you do things like drop dependent variables, or select your outcome, or add conditions, or get some more observations if you're just barely significant, then you can like raise your nominal false positive rate considerably, which for someone trying to get significance for publications would be good. And in general, would lower the rate of truth in the literature. And there's ample evidence that scientists do engage in these behaviors. I think we've all kind of been familiar with it. I was trained to do some of it during my master's. These aren't sort of like fringe things like falsifying data, but just common things that we, are taught to do or kind of have to do sometimes because there aren't a lot of options for getting a study out, right? This is an incentive problem and structural issue. So the solution that was proposed was to increase power and eliminate bias towards significance. And so this is like registered reports, pre-registration, power analyses. And we see this in this big paper called the Pre-Registration Revolution, which advocated for near ubiquitous pre-registration. They argued funders and journals should require it. They argued universities should require it in all but extreme cases. And that we needed to be coerced as researchers into pre-registering our findings to make sure we're not engaging in these QRPs, or if we do that, it's transparently guided. And they argued that pre-registration separates these hypothesis-generating exploratory studies from hypothesis testing, confirmatory studies. So you can still do the same things that would be considered p-hacking, but if you say it in the pre-registration, it becomes exploratory. They also argued for promoting an open research culture. So this is like sharing of data and code, but also describing your methods. This is sort of the open science movement. And its other big tenet is this notion of replication, which is conducting a study again, conceptually similar or exactly the same, and looking at significance. And this is also motivated by this model and this math. So, with 60% power and a 0.1 prior chance, and we've removed all this bias, there's a 75% chance that it's true. So this is like a medium-powered study being tested. 75% is great, but not perfect. And if we replicate it, we can work the math out again, just reiterating on Bayes' rule, and there's a 98% chance it's true. So under this math and under this model and this logic, replication, pre-registration, everything seems to fix this big problem that's rotting the core of science, and all of science is wrong. And so the idea really is that, science is facing some crisis wherein most of the literature is false, caused by widespread QRPs and selective publishing, reforming science through some revolution that encourages pre-registration, registered reports, open science, replication, and power analyses will improve replicability and ensure that published literature is true. As a social scientist, this looks like millenarianism, which is a type of social movement where a group proposes there's some big existential crisis that requires a societal transformation, and once that happens, you kind of usher in a golden age. Kind of reframe that a little bit, right? The world we inhabit has been corrupted through unethical behaviors of the many. And we've developed a set of rituals that will encourage piety and usher in a golden age of replicable research showing us the truth. Millenarian movements don't need to be wrong, but it has the flavor of it. And I think when we start to see these sort of cultural forces emerge, these sort of familiar structural dynamics, it's worth asking, like, is this true? Or are we just kind of getting ahead of ourselves? And so we're going to walk back to this core assumption, right? That effects are either true or false, that there are real effects and not real effects. So one thing that you can kind of guess is if it's a false positive, the true effect is exactly and precisely zero, then true knowledge should replicate with an arbitrary sign for the point estimate of the effect, right? If it's just a measurement error that you're getting, the next time you go to do it, the sign might flip half the time, right? And if you look at the data, that's not consistent, right? We see clear bias towards the direction of the original effect. This is like something in the very core of this model that's describing how we should reform science that doesn't actually match a qualitative aspect of the data that it's trying to fit and make sense of. The other big kind of component of this model is this pre-study odds of truth, right? Which depends a lot. If it's high pre-study odds, then there's no problem. If it's low, then there is. And estimates here suggest that 1 in 10 is the a priori rate of a thing you propose in psychology being a real effect, right? This is the kind of estimate. And so if we think about this and we plot the distribution of effects, it would look like this, right? 90% are exactly zero is the true effect. And the rest are somewhere sufficiently above zero to be a real effect, right? This is the kind of assumed distribution of effects that underlies this model that is at the center of scientific reform. And I think it looks silly. Does it seem plausible or consistent with your expectations of what effects look like in the real world? It's a rhetorical question, but worth dwelling on. And really, is this model consistent with productivity? So If we look in psychology, the average incoming professor has 16 papers, which for the ecologists here probably sounds quite depressing. But what would it take to get 16 papers with a 1 in 10 chance of everything you try being significant, especially when papers contain multiple experiments and statistical tests? Assuming the simple case where each paper is just one statistical test, you would need to run nearly 160 different experiments or conduct a lot of p-hacking to get a professorship in psychology, right? Under this model of scientific productivity. And for each of you, like, do you try 10 statistical tests before you find significance and then publish the paper? Like, p-hacking and QRPs happen, but that seems like an egregious amount for every single person who gets a professorship, right? Or is 90% of the research you've collected unpublished, right? All the times you go to the field, like is like 90% of the data points you've collected just sitting in a file drawer, never to be published because you got a null result and don't think you can publish it. Like, these to me don't seem plausible. And so, like, wait, where did that 1 in 10 number come from, right? That seems like a key thing. It comes from this paper where they tried to estimate that number, among other things, based on that data from the replication survey. And importantly, the size of the file drawer, the abundance of QRPs, this 1 in 10 number, is not measured. It's inferred because it's what you have to have for the false positives to explain replication failures. So this sort of whole idea, this formal model of scientific reform, is only true if we accept that earnest research findings rarely find their way into journals. And it's only in the motivation for it, the abundance of QRPs and file drawers depends entirely on this assumption that point nulls exist in the real world, and only thing we ever observe is sampling error. There's nothing else that biases our effect sizes. And if this were the case, if 90% of things that were produced were p-hacking or file drawer, would we expect to fix something like this with a form fillable PDF and some cultural change, some small norms, right? Like, I don't think that makes sense. But what if it isn't binary, right? So in this model, there's null effects. Literally nothing can exist between the null effect and a real effect in this model. And then real effects, right, with some small frequency. But these tall null effects, these like exactly zero effects, when we go to observe them, aren't going to be exactly zero in practice. Imagine you're running an exposure experiment, right? You can have sampling bias. The locations you chose aren't exactly the same as the ones you might choose in a different sense. Imperfect randomization, right? So you go to randomize your things, and that's only truly random at the infinite limit. Sensor errors, some of your cameras mess up. Your detection software for telling if there's an elephant there or not might fail. Recognize, a person walking by as an elephant or a bush. You have a misspecified statistical model. Sometimes we violate the expectations of our model. It's not correct or add a confound. QRPs and things we do also would impact the effect size. Imperfect experimental design. So I think a different way of thinking about this is a heterogeneity infused model, right? We assume kind of 3 sources of variability. The first is we hypothesize effects. This is the model in the paper that I'm going to talk about today. So we assume that maybe on average, there's no real effect. So our average hypothesis is quite small. And we just draw distributions of this. So sometimes we'll have a hypothesis with a large effect. Rarely, a lot of things we hypothesize might have small or medium-sized effects. Some are negative, some are positive. So you could relax this normal distribution assumption. It's not core to the model. It's just the easiest, simplest way to do the math. And then we assume this heterogeneity. So for a given effect, say the true effect that I care about is a 0.4 Cohen's d, when I go to measure it in different contexts with slightly different designs, different sensors, I get slightly different estimates of the effect size, right? This is all we're arguing in this paper. This is the core assumption, is that context-specific variation is going to shift around the thing we care about such that it's better characterized by a distribution of effects. And then sampling error, which, we just set to 1 for this. And if you put all these together, you get a normal distribution characterized by a variation that's the sum of those things, right? Cool. So all we really did here, we took this kind of assumed distribution of effects on the left and replaced it with a distribution on the right. And this is basically saying, what if we relax this assumption that there are true and false effects and just assume that we observe effects that are continuously varying? If we look at kind of our results, right, from that RVP study, you flip it and twist it, we don't see this massive spike at precisely 0 in the replications. We see a continuous distribution. So all we're saying is like, what if we relax back to that, you know? And if we have this model, we can estimate the proportion of studies that find significance. So in our model, the way in the paper, we say, what's the probability that a z-score drawn from this population with heterogeneity is greater than a critical value in a z-test. And a z-test here, the z-value, that should be z, yeah. The z-statistic is just a product of the sample size and the observed effect size over the sampling noise, which we have set up in here. If we just do this, it's basically a power analysis, but integrated across this distribution. Here's what we get. So we're going to see a lot of figures like this. For this one on the x-axis is the standard deviation of the hypothesized effect size distribution. And on the y-axis is the component of that sort of context-specific variation, right? So as we go up, we get things that vary more in context, and as we go to the right, we get fields that have larger effect sizes on average. And we find that either if something varies, or if you hypothesize big effects, you get significance more often than expected by chance. And so you wind up with much smaller file drawers in the presence of heterogeneity, that's misspelled, or even small average effects, right? And so here, the file drawer sizes, even at the far left of the graph, are just 4 to 1, smaller than the 10 to 1 estimate. And for anything else, it's made more like 1 to 1 or even less. So the file drawers disappear the moment we start thinking about heterogeneity in these effects. We can also ask kind of, how does the sample size play in here, right? So now on the x-axis, we have sample size. And as sample size goes larger, the chance of getting significance goes way up, even if you have small varying effects. And this is for a fixed tau of 0.2, which corresponds to Cohen's d. This is a small average effect in the field. We find that pretty much everything gets significance with enough sample size, right? The file drawers don't need to be very large. They still get null results 40% of the time or something. They're not uncommon. But, you know, the average paper will get significance. And so this model just relaxes this need to invoke a large file drawer. And then we can ask, okay, so if this were the way things worked, what proportion of stuff would replicate? So now we say, what's the probability that if I do the same exact thing again, that the second study will also get a significant z-value in the same direction as the original one, conditioned on the original one getting significance? And the math's all in the paper, it's publicly online, and we can work this out. So here again, we see the effect size tau on the x-axis and the varying effects on the y-axis. We find that replication rates are pretty low unless you have very small heterogeneity, right? So anywhere up relative to the effect size. So you only really get replication when the average proposed effects are much larger than the heterogeneity, which kind of makes sense when your signal is bigger than your noise. So it's not too strange to get low rates of replication. And so this kind of explains this idea of how we can get low replication rates, right? It makes sense if there's heterogeneity, because you go to test the thing again, the effect size shifts around a little bit and it doesn't replicate, right? It doesn't mean the effect isn't real. It just means that it isn't stable or necessarily consistent. And if we look across sample size, you know, we see this other really fascinating thing. And here, keep in mind that tau is 0.2. So you really need to have lower or larger average hypothesized effect sizes than the variation to reliably replicate. Otherwise, it's near 50–60%, which is what we observe in a lot of fields, right? And this is true no matter how much you increase the sample size. So even if I'm conducting experiments with 1,000, 2,000 individuals that get significance all of the time, if there's variation, I'm not going to have replication at high rates, right? So this model this is a deviation from the other model where if you increase power, you will ensure replication. Here we're saying there's a limit there. If it's too variable, you won't get replication. And so this is really an uncoupling of the file drawer from replication. So here, these two yellow arrows point to a space where effect sizes are small and there's not much variation. And you get about 60% replication. Here, the limiting factor is just getting significance because you don't have a lot of data. And up here, further up the graph, now you have giant effect sizes that are highly variable and the same amount of replication, right? So it's uncoupled from what we'd think it would be here. And our model also gets us this bias towards significance. This is not a perfect graph on the right. I made this in 4 minutes, but it just a quick sample of a model with some arbitrary parameters that kind of eyeballed to look right. And we get this sort of thing where the failed replications are biased towards the original effect, right? So we're qualitatively recovering kind of for free this feature of the replication data that's been missing from other models. But then we start to wonder, right? So, okay, this is great. Things vary, they don't replicate, but how often are they correct? You know, because we don't have a notion of a false positive, we need to think differently about what correct means. And one way to do that is to think about sign error, which is the probability that a claim published in a claimed effect published in some direction is the wrong direction. So how often in this world would things be wrong? And a nifty thing here is that not as often as you'd expect. So this is sign error, same kind of graph. And you know, for smaller amounts of variation, only less than 10% of things will be the wrong direction. You'll generally be correct when you get significance. And in fact, you kind of have to be correct more than half the time because it's a 50-50 chance, right? So science, the majority of science would be true in this case, in the sense of the directional claims made. This is, again, a totally different outcome. It's qualitatively different from the original model, and all we've done is relax one assumption. And if we increase sample size, we get a really cool and weird thing that happens, where increasing sample size can actually make sign error worse. And the idea here is that if you have a small sample size, you need to have your heterogeneity align with the true effect in order to get significance. But the chance that you'll get significance the other direction is really low, right? Because your real effect is biasing your observed effect against a type S error, a sign error. But with large sample size, you don't need that as much because the critical value for the z-test is smaller. This is a kind of a weird finding. It suggests that maybe increasing our sample size could actually make the literature worse in some cases, which is a strange and kind of counterintuitive thing. And it's a bit like stochastic resonance happening here. And we put these all together, we can do this sort of fun thing as well, where here we have a rate where things are highly variable with large effects. They replicate 50% of the time and sign error is high, right? And here we have smaller variations, similar sized effects, similar rate of replication, and much lower sign error, right? So now the file drawer, the correctness of the literature, and replication are all uncoupled or not coupled quite as we expect. And it really depends on where a field is, the kind of things they're hypothesizing, and how variable they are. And so, yeah, so at the same replication rate, we can see lower sign error in larger file drawers. And the other way of looking at this is magnitude error. This is probably more familiar. It's probability that claimed effect, this is the wrong description, sorry, is larger than the true effect, right? So this is an error in magnitude. And here we see that high heterogeneity inflates published effects. This makes sense, right? Because you have this additive component, and this is especially a problem when your real effects are small, then really what you're picking up on a lot of the time is heterogeneity causing significance. And as we increase sample size, we actually get a kind of a strange thing here too, where large sample sizes actually reduce magnitude error. So bigger sample sizes might make you less likely to get the correct direction, but more likely to get the correct magnitude, which is kind of a strange sort of trade-off that might be caused by sample size. And what about p-hacking? I'm not going to go too deep into this here, but in the paper, we look at one where you choose a post hoc alpha. So you run an experiment, you get like 0.08, and you're like, call it significant at 0.1, right? This is like considered a huge problem. And here we find it does something kind of different. It doesn't really increase the chance of type S error very much. In fact, at small sample sizes, it reduces it because it allows results to get into the literature that are preferentially selected for alignment between the real effect and heterogeneity. Whereas with magnitude error, it causes huge problems at small sample sizes, but at large sample sizes, this sort of kind of questionable research practice doesn't have the same effect. And in our paper, we show a few different examples of QRPs, some of which matter, some don't. Because the definition of QRPs really is predicated on the idea of a true false positive existing in the real world. All right, I'm gonna take a little breath here. So that's the model and the general ideas, right? And it's all we really did was we, the true models are a special case of this model. So we say just assume a normal distribution. They say it's sort of a mixture of two distributions, one that is exactly zero and one that is, non-zero, kind of like gamma distributed with like a 90% probability of one, a 10%. There's a much more complicated version of our model, which is a general version. We can make different distributional assumptions, and we could recover the original Ionidas model and our model by just changing the distribution, and we get those results back out. So it's important to see this is just a special case here, where we've relaxed this dichotomy. And in doing so, we see smaller file drawers with fewer QRPs are necessary, doesn't preclude them from existing. The model explains failed replications. It gets our bias back that we don't have from the other model, which is a qualitative feature. Most science is still correct. QRPs have very different effects than we expect. And replication may not indicate the correctness of the literature. And pre-registration and these sort of things might not improve replication, which is interesting. And replication might not need to be improved. And so this explains the key phenomena motivating scientific reform. Doesn't require these sort of big ontological claims about the size of file drawers or the impact of QRPs. And I think it better explains the observed effect sizes in replication experiments. And it really importantly, it doesn't require most of science to be wrong. So is it true? And then the answer is, I don't know. Who knows? It's a model, it's a rhetorical tool for thinking about these problems. But just relaxing this one assumption, and the whole story of scientific reform breaks down, which I think, especially as fields are starting to adopt these things and change the way we do science, it's worth taking a minute to say, are we reorganizing science based on a single assumption in a model, right? And would we? This seems like a big thing to do. Like, how could we be doing this with all these experts and such? We've done this actually in the past. So going way back to basic statistics, the p-value came out of this paper from Pearson. Also not a great guy, but was really popularized by Ronald Fisher, who I think it's worth mentioning. It was a founder of the Cambridge Eugenics Society, defended Nazi scientists after the war, and wrote against desegregation in the US. He was a big proponent of eugenics. That said, his tests were influential, and he developed these tests to address questions specific in biology. He assumed a point null, the same assumption underlying this model. This was then kind of bridged out by Neyman and Pearson, who thought about this more for decision-making and added this sort of threshold thing that we use today of 0.05. And this is basically what science works on, right? These were ideas in the early 20th century. And also they're just really built in this idea of the fixed null, which is fine as a modeling tool. But the question again that we have today is it real? And Jeffries, who is a name you might not have heard of unless you've done Bayesian stuff, showed some really elegant math that these frequentist things were just a special case of Bayesian inference. With a flat prior and some assumptions, you can get it back. He showed that you can always use the math of Bayesian statistics to provide equal or better results for any problem. This is like a proof here, not like a series of arguments. And that's more general and less restrictive. You can put different distributional assumptions in and make different claims. And he argued that Fisher's solutions, although okay for biology, were maybe not widely applicable to other fields. And I looked for controversial things about Jeffries. The most controversial one I could find is he didn't believe in plate tectonics, but it was like 1920s, so like he wasn't exactly alone. But whenever Jeffries tried to point this out, he was buried under an avalanche of criticism and simply ignored his mathematical demonstrations and attacked his ideology. Neyman also directed scathing ridicule at Jeffries far beyond what would have been called for, even if Neyman had been technically correct and Jeffries wrong. This is from James's book. But in Jeffries' words, there is no misunderstanding of Fisher, no heaping of scorn, no ideological sloganeering, only a bemused sense of humor at the whole business. And so I think the argument got us p-values based on an unwillingness to relax this null assumption and accept a more general model, and kind of a few people being bullies. This is my personal subjective take on the history of why we have things the way we are now. And so when I posted my paper a year ago, the response I got from Daniel Lakens was, your simple model is unrepresentative and meaningless. It teaches us nothing about real life replicability. I'm just like, hey, here's a paper I have. But he's like, the math is straightforward. My criticism is on point. The paper is very bad. Like just heaping scorn on this. It was like kind of oddly reminiscent, and several people actually responded to his thing and said this is not exactly nice. And actually, this phenomenon in meta-science, in this study of the replication crisis, has generated a paper by Mark Rubin called Questionable Meta-Science Practices, 2 of which are rejecting or ignoring criticism and superficially just being dismissive or mocking. So this phenomenon of like dismissing people's work in this space because it disagrees with this sort of view has actually been so problematic that it's turned into academic papers, and not just one, but multiple academic papers talking about how this space where these reforms are being developed is not particularly open to criticism from others and tends to be a bit prone to bullying. And like it kind of makes sense because these people rose to prominence. A lot of people that are arguing for these reforms or designed them basically single-handedly pointing at Amy Cuddy's work as like an example of everything that was wrong with science, right? This is what you probably all read about early on, the power posing stuff and whatnot. And they based their assumptions that she engaged in dodgy research on this thing called a P-curve, which also depends on this point null hypothesis being real. In our model, you can show that stuff like what she found in this order of things in the failed replication, this can all come right out of a varying effects model, right? So this assumption is behind this. And actually, if she existed today, because pre-registration spool is a plan out of prison, she could have pre-registered her studies and then deviated, done whatever she did, and had the exact same results, right? Nothing would have changed. It would have been completely normal. And even the things that are being accused of, like these data-dependent decisions, are really commonplace with pre-registered studies. So in this survey of them, 2 out of 27 pre-registered studies contain no deviation. So virtually all pre-registered studies deviate from their plan in a way that's the same thing technically as QRPs and p-hacking. It's just being disclosed. And in one study, all the derivations were disclosed. So only one study disclosed all the ways that it deviated from the pre-registration, and 9 disclosed none of them, right? So this fix to prevent people from doing things that depend on the data doesn't seem to be working, right? And it's just an ironic and strange space we've gotten into. I'm almost done. So these stats talks are, always kind of reminiscent of the same arguments happening over and over again between Bayesians and frequentists, and which is right and should you be one or the other. And I want to try to stay away from that and think about like why it matters. And the example that comes to mind for me is these cuties, wild dogs. That I saw with Kaya years ago. These are not my photo, but say you wanted to do a study on these, and you want to plan your whole PhD thesis to study these animals, right? You're going to do 4 to 5 years of data collection. You want to involve local scientists formed through collaborations as full co-authors and partners in the research. And you want to study social behavior, home ranges, impacts of weather, et cetera. You'll have GPS collars on them, be monitoring them with like audio recording and everything. It's a big, expansive study. Towards their conservation is the goal, and to make sure we understand what they need to survive as a species. So you got to pre-register it. Like, what do you pre-register? First and foremost, when you pre-register, there's a 4-year embargo, and then it's released with or without your decision making. So your research ideas will come out right towards the end of the your PhD as you're writing up your dissertation, and hopefully nothing in there can be used by someone else in a way that gets in the way of your career. Do you pre-register before you collect your data, right? What about the idea of involving locals as full partners in the research? Do you iteratively pre-register? What's your sample size? How do you do a power analysis here? How many dogs do you expect to see, right? Like it's just hard to squeeze this kind of question into the space. And then, your statistical models, your questions, and your inference goals, you're going to develop during your PhD. So how do you front load all the things that you plan on doing into this sort of work, right? I don't think it makes a lot of sense. And more importantly, what are the chances you can go all 5 years without deviating from anything you planned right before you started your experiment, And there are alternatives. So this is a principled Bayesian workflow that doesn't depend on calling your shot beforehand, but develops a valid inference model as you're going through your data and making sense of it and thinking through your inference goals and the generative process. And so you could have used this. And let's say you do, you abandon it and you now use this because it makes way more sense. And you've just learned it in your second year when a senior grad student does a seminar on Bayesian stats. Well, now your work's exploratory because you filed that pre-registration, right? It's considered that because you deviated. And importantly, you should read this paper. The confirmatory exploratory thing is entirely meaningless and it's just a heuristic and a choice that's made by some people in psychology in the way they view replications. It has no formal meaning whatsoever. But nonetheless, now when a strip mine comes along and wants to take away habitat that you have really good compelling evidence is essential for the species survival, they'll argue it's exploratory research, right? Not confirmatory. And you've downgraded that hard-earned research. And how are you going to confirm it? Convince another PhD student to spend 5 more years? And if it's a different 5 years, what if the population's changed and the effects are different, heterogeneous, and that doesn't replicate, right? Then they say it didn't replicate. So we wind up undermining the ability to study things like this if we're really, really wholesale embracing the kind of methods that psychologists with large, easy to gather sample sizes on MTurk have developed for addressing a problem that depends on this really, really simple, small assumption hidden in a model from 20 years ago. And what about Peter and Rosemary's finches, right? Could that study be pre-registered 40 years ago? They type out they're going to go here for 40 years and fund it every year and measure finches and then try to observe a speciation event. And this is how many birds they'll look at before it doesn't make any sense. This is a scientific question that cannot fit into the space. But I think at least a lot of us find their work compelling. I certainly do. What about climate change? There's only one world, right? One Earth. The sample size is one. Our understanding is developed through different ways of thinking about data than what fits into this sort of square. Is climate change work exploratory at this point in time? Is that a healthy thing to say? I don't think so. And more generally, any poorly understood phenomena, right? So rare diseases, rare events, lots of things in biology, ecology, and evolution. And rare and vulnerable populations of people, of animals, of really anything that is rare or vulnerable is going to be really, really hard to study and fit into this space. And so how might this simple assumption that if we relax makes a very different world change what we study, who benefits, and what's considered good research? And so I think, it's heretical to say, but I think scientific reform is dangerous in some ways, prioritizing the abundant, safe, and well understood over the rare and vulnerable and poorly understood. And I think that these, this may kind of reinforce existing power dynamics that shape what science studies and who benefits, much as they did 100 years ago when eugenicists clinging to the same assumption determined how we've done stats for the last 100 years. And so I think before we adopt these things, we should conduct a power analysis. Thanks. Whew. Feel free to start yelling at me too. I feel like that might happen.
Thank you very much, Joe. For those of you who may be joining us for the first time, and for those of you joining us through the YouTube channel of the Fine Seminar, let me remind you how we're going to proceed from now. We ask that you please only type a question mark in the chatting window, and I will be taking in your questions in the order that they appear in my chatting window with a question mark. If you are watching us through YouTube, you can please write the question and I'll read it. We have a history. We were very proud of giving priority to students and postdocs to pose their questions. So if you want to make it clear that you are a student or a postdoc in case I don't recognize you, or you know how Zoom still moves and sometimes I don't see where the questions are coming from, just type a P or an S for student and I'll give you priority in asking the question. With that, I just want to open the floor for questions or comments. Joe told us when he started that he was hoping to get a lot of conversation and exchange of ideas. I think we probably saw it was unusual to talk because we probably had more questions on the slides than answers. And I think that speaks probably to Joe's goal with this. And I hope that you will agree that there are lots and lots of things that we could discuss. So with that, once again, Joe, I thank you. And I'm going to open my chatting window and make sure that I don't forget anyone. It looks like Kaya, who is a postdoc, has the first question. Kaya.
Before Kaya jumps in, I want to answer the question about QRPs. I mentioned it a lot and took for granted that it was a well-known term. It refers to anything that could increase the chance of a false positive. So it's stuff like changing your alpha afterwards, selective reporting, p-hacking in like overt ways, and also like things like outright fraud. So it's a term used to encompass all the things that might increase false positives.
Which I have to say I checked, questionable research practices. For those of you for whom English may not be your language, that's what QRPs stand for. Kaya, you have the floor for the first question.
Thank you. I mean, I did the introduction, but I'll still say, hi, I'm Kaya Tombeck, postdoc at Hunter College, just to start that practice up while asking questions. That was a really cool talk, Joe. Thank you so much. Made me think a lot. And I like how you're challenging the fundamentals here about what we're doing. I have a kind of a hard question, so feel free to, skirt around it. But do you think it's a coincidence that Pearson and Fisher kind of simplified the stats that we're doing into the sort of more binary thinking, and that they were also highly bigoted? Like, is there a connection in terms of like simplifying the world and like categorizing people, and was there some kind of alignment there in terms of worldview and statistics?
Yeah, I mean, I can never know my way in their head, but so all that said, I think that, it's pretty convenient for eugenicists to develop a system that is painted as objective truths about the world rather than subjectively implemented numerical procedures, because then when you find a difference, which is the main thing, you don't care how big it is, you just want to know if it's significant, right? So you can say one is lower or higher, which is kind of the thing you want to do as like, I don't know if it was intended, but it certainly was convenient for their ideology. And I think it definitely has demonstrably been weaponized over the last 100 years to further racism. Still is today in many ways.
Yeah, that makes sense too. I think that's a great.
They were lucky or intended. Yeah.
Okay, the next question is from Amy. I remind you, please introduce yourself like Kaya did, if you can say your name and tell us where you are. Amy Schlicht, I hope I'm pronouncing your last name well. You're next.
Yes, thank you. My name is Emmy Schlicht, and I'm working on blue tits in Bavaria in southern Germany at the Max Planck Institute for Biological Intelligence. Thanks for this very interesting talk. It was super interesting and very thought-provoking. I have two questions, actually. The first one is a question and a comment. I'm personally a great fan of pre-registration, but I think it's completely non-applicable to descriptive, exploratory, observational, whatever you want to call it, work, where you sort of try to find something, try to explore the world, but I think it's completely useful for trying to establish something where you already have a very good idea about what's going on. And then I think it's a great idea to pre-register it. So in that context, I was wondering, is there anything wrong with pre-registering stuff? So that's why one question. The other one is I'm trying to wrap my mind around this heterogeneity of effect sizes. So let's assume that because biologically, I tend to think about something as either being, let's say I'm testing a relationship, and I think biologically, I either expect it to exist as a biological relationship, or maybe it's not related. There's no relationship. And what you depicted was somehow a variation around that. I do understand that statistically everything is stochastic, so I will always measure something. But what does it mean conceptually that if there's this variation around zero, is there a relationship or is there no relationship biologically speaking? That's my second question.
The first question on pre-registration, I think like as as a pedagogical process or like an idea clarifying process, I don't see any problem with writing your ideas down ahead of time. Like, I think most of us should probably have a plan when we go to do research. I think on like the is there any downside, it depends a bunch on a lot of the area. So, you know, if the work is anything other than doing the same thing you've already done, and there's any chance you might have to think differently about your analysis or how you're going to characterize the data, I think there maybe is some risk that you lock yourself into a thing that maybe isn't correct, because then now it is considered confirmatory, right? So there's, I think, create some incentives to stick with possibly flawed models that I think need to be explored and studied. This isn't a claim that it does, but a claim that it could. And I think that what I'm more concerned about is the promises associated with things like registration and registry reports, that in eliminating bias, they can make, you know, more reproducible, correct literature, and that they distinguish between exploratory and confirmatory research. So my bigger concern isn't so much like whether or not people write their ideas down, but the way it's sold is that and a tool for transparency, when it's like really quite clear that people don't even disclose things, and you have to really carefully read it and hope that it's clear enough in order to maybe find it doesn't seem to serve its purpose in the way we want it to. So I think it's all undersold, oversold, and underdelivered. On the like notion of effect sizes, I mean, there are certainly things that are truly neutral, right? Like they're biologically inert compounds, right? But it's not just the direct effect, but everything that leads to the observation. So the imperfect randomization of your groups, a little slightly bad fit for your distribution to your statistical model could cause this, adding in some inadvertent confounds as predictors to your model, sort of even the decisions to like drop data points, right? Any of these sort of things that might make the effect size wiggle a little bit when you go to measure it could be considered heterogeneity. So even like for a truly biologically inert thing that's, you know, has no impact whatsoever, anything that might shift around that estimate is going to cause heterogeneity. In some cases, it might be really small. I bet in physics, it's tiny, right? Very small heterogeneity. But like in my research on social media, it's huge. So I think it depends a lot on the field.
Thank
Good
you.
question. Great questions.
Thank you, Joe. I think I'm next, and you may have seen that I just posted in the chatting window a book that it goes mainly to those of you who are not, most of us have not done a lot of reading. The couple of chapters that they have in that book describing the history of Fisher, I've always found very useful. And I know it's an old book and there's so much that sometimes we don't know what to read, but I still find it extremely useful in assigning chapters to students, because it has a little bit of everything for everyone across disciplines and fields. So I strongly recommend to check out that book. Joe, you were encouraging productive disagreement. I think that what I'm going to say is probably unproductive disagreement, because I'm no historian. But I would try to stay away of putting too much weight on whatever Fisher did. I mean, if we're still doing things today, we cannot blame it on something that one person did 80 years ago, right? I mean, nobody would dream of blaming those who were promoting smoking if they're still smoking today and getting lung cancer. So the question that has puzzled statisticians trying to revert, to move us away from null hypothesis significance testing is, why haven't we been able to actually produce a change on people's minds and statisticians? Whatever reasons they had, again, no historian, like you said, I cannot be in his brain, and I'm always a little bit reluctant on making quick conclusions and using big words to describe things that happened 80 years ago without being a historian. If we're scientists for the wild dogs, we could also be very, very data oriented in making judgments of what motivated people such a long time ago. But why? I mean, we still have such a hard time getting people to transition to a non-binary approach to the evidence we gather. For me, I don't know, that's a psychology question, a sociology question. I know people have done a lot of research trying to understand that.
Yeah, I mean, my take on this is it's like this gets to my collective behavior roots, right? So initially when these methods started being adopted, it was like, what do we do? What's best? There's a back and forth, right? It's still not crystallized. But once you start getting norms in like an accepted sort, like once those norms get built and structured, that initial like argument and how well it goes might have a cascading effect later. And, you know, maybe say we learn that it's much safer to drive on the left side of the road than the right side of the road. You know, for example, changing that would be extremely hard, right? There's this infrastructure, there's memory in the system. There's people that are already trained in this way and don't have time to retrain. Like, who can learn a different way of doing stats midway through their career and take 2 years off from teaching and everything else to dig deep into McElderly's book and start to apply? It's very hard. And so I think that, you know, part of it probably is fundamental tendency for us to dichotomize things in our brain. Part of it is the desire of knowing what's true and what's not true, so that we really want the point null to be true. This is not a real effect, or it is a real effect. And part of it is probably just like the structure that got created and the momentum of the system. I think it's really interesting.
I agree. I mean, the way you were describing it was making me think about the paper that Richard McElrath with some colleagues that I feel bad, I don't remember the names, published on the natural selection of bad science, right? Because these choices of one way of doing it, of course, they're going to be very difficult to get changed if the system is rewarding. And it has been rewarding for 80 years, as you described so well today.
One of the kind of interesting take-homes, I think, from the model we have too, that I didn't get into as much, is that it might be the case that it's okay to use p-values in significance testing in some contexts, because we find that, you know, a lot of the research is correct in direction and magnitude, right? It might actually function pretty okay as a signal detector, which is a little counterintuitive. So even though the assumption might be wrong in the meta-scientific sense, of like the models, it's not abundantly clear that it can't work for science, right? Despite its flaws. And I think it's also resolved some of the tension around like how science seems to progress pretty well a lot of the time, despite being really reliant on tools that have kind of well-documented flaws. That's my follow-up.
I don't see. I'll make one. I'll share one more comment while we wait for somebody else to have question. As a teacher, interacting and talking to young scholars, to students, one of the reasons that I think it is so hard to move away from the binary is that what I'm asking them, what actually I'm asking my colleagues, I'm asking everyone, is take responsibility for deciding what's important about your study. When I do the binary, it isn't me who says this is important, but it's a number. It's a threshold, is the computer output. Whereas if you flip it, and if we start asking the author submitting, if you start asking the student, please help me understand why this is meaningful, then you cannot answer those questions unless you start moving away from the binary to a continuous effect size variability and try to see how that relates to the questions you have. And the students get paralyzed, because if I had an undergrad bringing the paper with a bunch of p-values and I said, forget about that, you tell me what you think is going on, that's difficult, of course.
Yeah, I mean, and this kind of relates to a thing that was in my early training that I initially, when I was taught it by my master's advisor, thought like we need stats, but now it's just abundantly clear. She always said, when you have sorry, cat's getting fed. When you have a graph that has compelling data and the raw data are plotted and it's obvious the effect, like, you don't really need stats, you know? So you only kind of wind up using statistics when you wind up in this place of, like, at least in terms of trying to prove something's true or not, when you wind up in the uncertain space. And it's kind of interesting that we don't wind up just saying it's uncertain. Not only, but like that often the way when we really are leaning on a p-value to make a decision, it's in a case where it's uncertain in some way. This is like poorly explained answer, but your point is well taken, that I think that the ability to subjective, like the importance of understanding that these are subjective decisions we make about what's going on needs to be kept in mind, and that the little robots can't tell us answers every time. Like, we have to interpret them.
Subjective. I mean, but I've had students look at me saying, what do you mean the decisions are going to be subjective, right? Mm-hmm. I mean, no, I mean, it is supposed to be subjective. And when I've talked to my statisticians colleagues and I asked them, isn't statistics the science of uncertainty and probability? right? But most of us are going to test. We're going to statistics for certainty, but what they do is quantify uncertainty. What they do is estimate probabilities. By definition, there's no certainty in probability. Anyway, Kaya, you're next.
I guess I'm wondering, Joe, so I think there are some contexts that you'll probably agree, do require pre-registration, like clinical trials. Clearly they're operating with a lot more former knowledge and high stakes and highly controlled conditions. But for a field like us, I mean, we're like, ecology, if I'm not wrong, was coined in the 60s. Like, we're just going to be in flux for a while. We're going to be uncertain about a lot of things, a lot of big fundamentals for a while. What do you see as, I guess, kind of just like a more efficient way to filter through all the crap we have to, like all the information, all the variation? How can we better organize ourselves? Do you have some kind of, vision or like principles that you've been thinking about to follow?
Yeah, so to your first part of your comment, I think that's something actually I should have brought up during the talk, which is that there are absolutely contexts where you need something like clinical trial registries. The industry influence and deciding on patents and their incentive structures are so strong that there was ample evidence that they were fudging stuff to get drugs through, right? So that transparency is absolutely necessary there. And it's very doable because you have pretty predictable distributions of effects, right? Simple models, it's A/B tests, right? It usually comes after a pilot. I think like in corners of science where you have ample data, simple models and straightforward experiments, then and especially when the incentives are aligned to get certain kinds of results, like a direction of a result, the drug works, for example, I think you probably need something like pre-registration in those cases. But the idea that it's ubiquitously beneficial, I think, has been questioned numerous times in the literature, and those papers don't get cited by proponents of registration. So I think that's something that needs to be discussed more. And your second point is like, how do we deal with all the complexity of everything? Great question, Kaya, very answerable. I think this is, where we have to kind of like take a step back and say that like, fundamentally what statistics is using probability theory to make sense of data and try to learn something from it, right? Like start from there and then figure out what aspect of probability theory might clarify the questions we have, right? So do you need a Bayesian model that you can express some ecological model, right? Like you want to do like predator-prey dynamics, you can code that into a model and get parameters with HMC or something. I think McElrath has examples of this. Are you running a clinical trial where you need to show that something like significance or because the norms there dictate it for public trust and such. Like what, I think we just have to take the whole toolbox of things, like not just frequentist versus Bayesian, and we have to, unfortunately, like learn enough about it and the thing we care about to combine them in ways that get us insight. And it's never going to be perfect, but I think it's also important to say like, well, maybe I won't always get everything correct all the time.
I mean, maybe this part of the solution is bigger teams. Like physics they have papers with 1,500 co-authors sometimes. They're working, with huge teams to advance their knowledge, and we can expand a bit to have some specialists that can really help us with certain stats that fit our question and our data. I mean, I think we're already a collaborative field, relatively speaking, but I think sort of just allowing that kind of control to be a bit more distributed across the authors might be a solution.
Yeah, I agree. There's other questions in the chat too, so I might grab those in case anyone has to leave before noon, and also because you know how to call me.
Yep. So the next question is from Karsten.
Yes, hello. My name is Carsten Schradin, a researcher at the CNRS in Strasbourg, France, working on social evolution in mammals, mainly in South Africa. I don't have a proper question. I don't even have a proper comment, but I still wanted to say a little bit to Eduardo's question, why we still keep on having p-values. Of course, your approach to ask people reading the study and the data, what does it really mean for you? What is the importance of this study might be very valuable, independent of the p-value. But the risk here is somehow when people just come up with what is important for them, then they might go away from the data totally. And so the p-value at least is one way to indicate whether there is something behind it or not. I mean, before this was used in behavioral ecology, and still these days, often the important big professors have their opinions. What is important, what is interesting, and what is the truth based on some anecdotes they came up with some ideas. And this can lead to problems. I mean, when we look at our own discipline, Konrad Lorenz, when you read his books, many of these things are based on anecdotes and are not correct these days anymore. But then, of course, science progressed and people tested these hypotheses and other things with statistics, and this is how scientific progress came along. The other problem is when you go outside of the field of science, but still fields which the public sees as science, like people having corona denial or not believing in climate change, when these people come up with cherry picking and false or single experts and tell this is important and climate change does not really exist and these data you can interpret differently, this is also then one way we can come into problems. So many results I read with the p-values I do not believe, including some results of my own students. I still have to publish it as significant because students need papers. But I still think there can be some positive things to having one value which people can look at whether this has some importance or not, and that is relatively easily understandable. So I think we need both. We need to understand what the data mean and whether it's important or not, independent of the p-value. But some criteria of quality like the p-value, I think it's very difficult to get rid of it because you get a lot of problems into the system otherwise, which we had before with some of our best experts that really brought the field forward, and which we currently have by people like that denial corona, climate change, and so on.
Yeah, just to kind of like feed on that a little bit, I think that this is an interesting sort of touch on thing here. And one of the reasons why it's hard to move stuff away is that because we kind of rely on these tools to make definitive claims, we then build ourselves and our careers in those claims, right? And so a lot of us as scientists, the stuff we publish, the claims we've made, they hinge on the p-value thing working, right? And so if we, to relax the idea that it's maybe always correct, or the best way to model something, I think does sort of cause us to have to give up something about what we've learned, which is hard. And the other thing I just want to mention is, like, if you go through this preprint, a kind of corollary of this is that it might be okay, even just the p-values might not be a problem. The bigger issues might be things like model specification, confounding, like these sort of things probably concern me more than like noise from p-values, or even honestly some forms of questionable research practices, which we look at a little bit in the thing. Very long topic, but I think it's really mostly unclear to me, like, how we should do science best given what people are willing to do. And yeah, we'll see.
Thank you, Joe. Thank you, Karsten. The next question is from Rag.
Thank you. I am Raghvendra Gadakar from Indian Institute of Science. Thank you for this talk. I enjoyed it, but I must confess that it will take a lot more effort for me to really understand what you're saying, let alone agree or disagree. It will take a lot more effort. But even before I do that, the general disturbing feeling that I get from your talk and from talking to many other people is that even those of us who are not consciously practicing any form of QRP, we're still not doing things okay. We could do things much better. We're not doing okay. We use p-values, and that may or may not be the right thing to do. So it would be very helpful if someone like you gives us a reading list of 4 or 5 papers where things are done right, which I can read, understand, give it to my students and say, this is how we should be doing things and not the way we have been doing in the past. Is such a thing possible?
So I'm gonna first, I honestly don't fully understand my paper either, if that helps at all. Then I'll kind of prime the rest of my answer, which is that I think, I think the thing is that it's really hard to know what doing right is, right? Like, we think about all the ways science studies stuff, from photos of black holes to measuring evolution over long time scales to combating disease and developing vaccines and running trials. like it's a lot of different spaces that we're trying to apply probability theory in to make sense of the world. And like what the right way to do it is, I think we get too lost sometimes in these kind of arguments about like you should or shouldn't use p-values. And we kind of forget that like there unfortunately may not be a best practices. That said, Richard McElreath's book, Statistical Rethinking, is a good start, and less opinionated and non-Bayesian. Regression and Other Stories is also quite good. And there was another one that came out recently that I can't recall. It looked fantastic. I think this sort of corner of literature, rather than trying to tell you what to do, empowers you to figure it out in that context as you go. And so I think ultimately the right thing to do is going to be something you have to kind of figure out for your questions in the field you're working in, and you're never going to get it fully right. The hope is that you just learn something a bit, and then the next time, I think walking forward with that humility that maybe I'm wrong, like maybe my entire model I just shared is entirely wrong and I'm way off base. I think that sort of space is probably the best way to go about things.
Yes, but it would also be very helpful if somebody can flag 1 or 2 papers. I mean, the books give you the philosophy, but I like to read some model papers which do things right.
Yeah. Oh, I will scratch my head on that and send them around. If I can think of any papers that like I can say are definitely correct. There are some very great papers out there. But yeah, I'll see what I can find.
But how about, thank you both, but how about if because we should also, I mean, I don't think Rag is asking for something that's correct.
Yeah.
It's asking for something that, so your student comes and says, oh, gee, I need to do a PhD dissertation. I have no clue what it should look like. And so we go to the library and we pull out a few dissertation. Our student will do a dissertation that's going to be very different, but we can sort out dissertations that we say, see, this one is well structured, and there are papers. And I think what I'd like to suggest or ask, please email me if you have examples of papers that you have found useful, because sometimes you may say, what I liked of this one is that something, for example, that I'm pushing for in my own work is that we start doing what sociologists and political scientists do much more than we do, which is have a whole section on limitations. And the limitations can go anywhere from what Joe said, that I thought I would be studying wild dogs for 5 years, but you know what, there was a pandemic. So now I ended up studying them 1 year, right? That's a very, all of us can relate to those limitations. To having tables where we literally list every single variable and we have definitions for the variables. Or we define the population of interest. So I invite you to send me, my commitment is that I'll put together the list of papers that were shared, and maybe we can even make them available in the Frontiers in the FINE website. But I totally agree with you, Rag. We need examples. There's one paper that I'll share right away by Barney. Tony, help me out. Barney's last name. Mary Ladbeck. Right. This is a paper that goes back 10 or 12 years, but I loved it because Barney looked at the same data set in the same paper and illustrates the conclusions he would have reached with a frequentist binary decision. The frequentist is not the problem. The p-value is not the problem. He compared what are the conclusions. If I just go with 0.05, I do this, 0.06, I do that, and then analyze that, not with Bayesian, he wasn't doing Bayesian, but he took a kind of information theory approach, multimodal approach, etc. So I agree with you, Drag. We need those examples. Let's look for them and share them.
Yeah, I'll keep my eyes peeled too.
I have a quick question for Eduardo. These things that we get in the chat, are they somehow archived?
Oh, that's a nice reminder. Somebody can help me. I know that I can export the chat. Will I be able, but I imagine I need to do that before I close the session, right? Can somebody answer that? What I'll do is I'll save the chatting and then send it to you, Rag. I don't know how people would feel. I don't mind that people know what I wrote. But I'll definitely send it to you, Drag, and I can definitely share these papers with you and those who want to get them. Just let me know.
Okay, but more generally for all the previous sessions, very useful information in the chat. But as soon as I leave my Zoom meeting, it's all gone. And as much as possible, I try to copy into my notes, but not always. So if this can be archived in some way, it would be very nice.
Can everyone am I the only one who can save the chatting as the host, or anybody can save the chatting? Do you guys know?
Eduardo, this is Ron. It'll save as the host when you close the Zoom session. It will save the chat somewhere on your drive,
Right.
and then it's in a .txt format, and then you could do with it what you want. And one interesting thing about chats that not everybody knows is that private chats between two people, like not back and forth with the host or with everyone, but private chats, if they're allowed on the Zoom, are also in that .txt file.
Okay.
Okay.
Oh no, I didn't know that. Not from this talk, but from I haven't.
Good to know that. Okay, let's go. Xingyu, please. We have a question from, I think you're next. Yes?
Yeah, hello. I'm Jingyu from the University of Strasbourg. Also, I'm a PhD student of Carson. I'm also working on small within in South Africa. So I have a very specific question about one of the slides you have. It's the one about Bayesian method. So I remember one sentence was that Bayesian method can apply to most of the situation in biology. So my question is, why particularly in biology, why it works so well in this field?
Oh yeah, so I didn't explain that very well, I don't think. So basically, Fisher was really interested in questions that were in biology and kind of specific with certain kinds of like thinking like two plots of like different treatments for plant growth, like those kind of simple things with simple comparisons. And he developed these statistical models like say t-tests or ANOVA that were based in these sort of ideas. And the models that Jeffries had developed were more general purpose. And Jeffries showed that you could actually take the general purpose model and add some specifications and get the same thing that Fisher found, but also have a lot more extensibility outside of biology. So he showed that all these models that Fisher developed in biology were special cases of very general principles that could be applied. And so the stats work broadly everywhere, but I think the point Jeffries was kind of making was that the things that Fisher had developed and the epistemology he developed was really rooted in the way he thought about biology and wasn't thinking as expansively, and that his problems were actually much smaller than these sort of broader problems of inference across everything. That's my interpretation of it, as not a historian either.
Okay, so the reason why biologists like to use it because the method itself was originally designed for biologists.
Yeah, exactly. It was kind of, and like I think a lot of the papers in biology, like early papers, made big jumps forward using it. It was useful. I think that's important to note too. So I think, and then other fields it spread to as well. So I think these statistics that started in biology now are parts of basically all of science in different ways. So we saw it kind of spread outwards in an odd way.
Okay, thank you.
Do we have any other questions or comments?
Everyone's been so polite. I was expecting at least one person to be upset. This is a really nice group. Since I moved over to social sciences from, is the recording still going on? Or the live stream?
Yes. Yes.
Okay. Well, I'll save that comment for later. But I'll suffice it. I miss ecologists quite a bit. I like social science, but the friendliness in ecology is refreshing.
Karsten.
So I take the liberty to ask one or two more questions. at the beginning of your talk, I mean, you showed that there might be no replication crisis, but I mean, there definitely are papers that are and have been influential that could not be replicated, that are some kind of very critical and damaging. So how shall we identify those and what to do about this? And I think even worse is that some of them have been so influential that they influence an entire research field, that in future only studies that support this idea are published, even though for decades we could know either it's not true or at least it's not, to go to Eduardo, there is a little bit, but it's not really important and meaningful. And I'm also not saying here during the recording which research field I mean, but there's also some in physiology and behavior that I'm thinking about.
I think that's well anonymized because there's a lot of fields like this. I think you're right. This is one of the parts of our model that we don't really go into, is that like it's obviously bad things happen in science and wrong things get published and it causes harm. I don't think we're doubting that at all. I think you know, one way to get around that is not to weigh too heavily on big prominent studies, and when a study starts generating the backbone of a field, to be willing to question it. Like, this is a sociological problem that you're mentioning here. It's a structural problem. I don't think we're ever going to be able to get rid of wrong results. I think, and if we could, I don't think we'd want to. So I think sometimes the wrong results are really generative, right? A paper that's completely wrong might cause a whole field that is itself wrong, or it might actually generate a response discussion that makes things more interesting, right? So I think it's okay to have wrong papers sometimes, as weird as that sounds. And it's easier to tolerate those, I think, if we have a bit of humility about how much we can learn from a single study in a single context put out by a single group of people. And so I think, you know, in a sense, like I am replication in a really broad sense of like, we should have a coherent structures that link our papers together the way we think and talk about them is fantastic. And in theory generation, so yeah, and I think the other part of this that probably kicks in here is the notion of thinking about incentive structures, right? So this is where I think we really get in trouble, the incentive structures in science. So if we look at some of the really high profile stuff in our field, we had pretty outright fraud in social behavior that happened and was documented and was a big issue, and we all know all about this. You know, it's easy to chalk things up to bad actors, but I think, like, what are the incentive structures, the pressures that either reward people that do those things or encourage them to do them in the first place? And what checks can we have for these sort of egregious things? I think we probably do need forms of science reform, and we can always think about iteratively improving the process of science production and trust and such. But I think if we are doing so around a specific model of what's wrong and how to fix it, we might wind up somewhere different than if we're thinking a bit more broadly.
And then I can maybe have one more question. I don't know if you understand it fully. But what always surprises me is when we look at different research groups, also how their p-values differ. There are some extremely successful research groups always publishing papers with the clearest results in the clearest journals. Would be interesting to do a study on how p-values between one research groups fluctuating and whether this is normal and expected or not.
Yeah, so this is a super interesting part of the talk that I did not get into, but I need, because the modeling is not done yet. So this is all very tentative. And if someone else sees this on YouTube and decides to do it, please let me know so I don't waste time. But if you have heterogeneity, you get kind of very different assumptions about p-values and results. And one of the things that really drives your significance down is just having a larger sample size, right? If there's heterogeneity, if the true null isn't true, then a little effect size you get is gonna run your p-value towards zero quickly as your sample size goes up, right? So I think one of the big differences is just like who has more money for experiments is gonna be a thing here as well. And then the sort of stuff from like the data quality, like the p-curve things, these assumptions that p-values are more likely to be near zero than lower. It gets kind of odd because with heterogeneous small effects, you actually get more expected values near 0.0405 than you'd expect by the other model. And so some of the ways we think about the distribution of p-values, what they should be in earnest research, is actually quite different if we have these heterogeneous near zero effects. And so I think one of the really important directions for follow-up work is thinking about what, thinking about what this implies for detection methods for things like fraud and abuse.
I just shared the chat, and I don't know how many of you know about this initiative by Yuri Simonson. Joe mentioned one of the papers he published some time ago. He was at Penn when I was there. And I thought, we had a panel by editors. It'd be interesting to hear from the editors. If some of us decided to really give many of our data sets that have already been published to an initiative like Data Colada and say, listen, you know what? Look at the data again. Same data, I've already got it published. And yes, I'm up for surprises, because if they do it differently, if they do it the way they think should be done, they may find that whatever I concluded before has absolutely no weight, etc. But it would be fantastic. Thinking about what you're saying, Carsten, not going, maybe the first way to do it is not trying to look at other people's research, but why not start by looking into your own research and say, listen, this is what we've done. Here are the 30 papers. I'll provide you with all the data you want. Look it inside out as much as you can and tell us if it holds.
What's
and
interesting?
Then, of course, yes, go ahead.
This is super fascinating you bring this up. So there's a talk by Richard Morey where he talked about this as well, like the idea of red teams that come after your data afterwards to verify the findings. And one of the problems that emerges is the same incentive structures to p-hack come up in the null hacking, right? You already have the data, you've already seen the results, and then you're coming up with a model trying to get a conclusion that the result was, say, null, right? And so you can actually wind up null hacking against the results. And often the incentive structure is set up to try to find a model that gets a null result, right? So it's kind of a fascinating other side of the coin that the data police that want to to push back against your thing actually can wind up engaging in the same sorts of behaviors that would increase false positives, but increasing false negatives.
No, but what I was thinking is, I'm thinking of that paper that was published in PNAS a couple of years ago, where I'm thinking more, going even further back into the process. The people who take on my data have no idea of the analysis that I did. If you were to get this data, what would you do? Right? Because what we know already is that different sets of analysts will come up with different structures, different approaches to looking at the same data.
Yeah,
already there.
Yeah, I think that idea is really cool. And I think one of the ways that I would love to see this play out is in some of the Bayesian work, you can do model averaging. So you have multiple models that say each analyst generates, and then you can kind of weigh them against one another with different model comparison tools like Wake or and you could add a weighted average model of the thing you care about. And so science could work that way, where you actually not only no longer have a single model, but you have a population weighted model across scientists with similar training and domain knowledge. For some questions, that might be a really cool way to get at it. I think it'd be awesome to see.
Thank you, David. That's a good idea. So we have it there. Yes, Suleima, you're next.
Yeah, hi. Suleima Tang Martinez, retired from the University of Missouri in St. Louis. And I think I may have a disagreement with Eduardo, but I'm not sure because I'm not totally clear with what you said, but it relates to the very first question you asked today. And if I understood you correctly, I thought you said that you didn't think it was important to look at the motivation of people from the past or political values of people from the past and to concentrate just on the present. Is that correct? Or did I misunderstand you?
No. I said that I'm no historian. I said that doing that it's a whole career and initiative, and people are doing it, and people have looked at, if any, Ronald Fisher's life and history. So I'm sure there's an awful lot. What I'm reluctant is to, because I'm no historian, because that is as serious an endeavor as any of our studies is, to kind of make quick conclusions about what they were or they were not. And also because for anybody's history, we're going to have several views on what any given person did or did not. And when it gets even more complicated, it may be clear what that person did. All of us are always in the search for causality, reaching conclusions and finding evidence for what that person did actually caused or was related to what happened in the following 80 years. That's a big undertaking. That's what I'm saying.
Okay. Yeah, because I mean, I personally think that as scientists, it is extremely important for us to know the history of the past.
Yeah.
And I mean, I guess I believe that we're scientists, but that our political and social values very much influence our science. And at the same time, that our science can then influence social and political values of not only of us, but of society in general. And so they can have extremely important and dominant effects on society, especially like in the case of Fisher, for example, when their work essentially becomes dogma for our work as scientists. And Fisher obviously is not the only one. There's many, and we can talk about eugenics, and we can talk about racism, we can talk about anti-Semitism, we can talk about sexism. I think it almost behooves us as scientists to be informed and to very seriously look at the work that, as you said, historians are doing. And obviously we can't 100% say that, you know, Fisher's views on eugenics or on the Nazis necessarily causes everything else that has happened since with you know, p-values and so on. But I do think that it is important both in understanding the factors that might have, if not cost, at least help to influence our perceptions and the way that people respond so negatively when you critique some of these ideas about the, you know, about statistical significance and so on. But also because I think it helps us to examine our own work, our own values, and how our own particular individual biases or beliefs might be influencing our own work, and to try to guard against, you know, influences that shouldn't be there. So I just wanted to say that, and I wasn't sure exactly what you had meant when you made your comment, but I just wanted to throw that out. And I know it's a little bit of a tangent, but since our speaker brought it up,
right? Yeah.
and we don't, I think we're a sufficiently informal group that we can get off into tangents, and this is, you know, related. So I decided to make the comment.
Absolutely. No. Who? I'll stop. Joe, you go.
I want to just clarify that I disagree with you a little bit. It isn't a tangent. It's very much on topic. That's my one disagreement, but otherwise I completely agree.
Yeah,
I was going to say the same, because that it is not a tangent, that it is central, actually speaks even further to why a binary, irrational decision on the relevance of your research is stupid. It's meaningless. I mean, how is it possible that if we're acknowledging all the complexities that are playing on these biological systems, they were going to make a yes-no decision? So
Yeah.
it isn't tangent at all, because in the case of Fisher, it could have been society, etc. But we know that for every single living organism we study, we have a whole range of potential factors that interfering with everything that we were able to measure. So it's the heterogeneity that Joe was discussing. I need to get that. It was a 2018 paper you mentioned, Joe, when you were describing the many sources of heterogeneity, but I didn't get the last name towards the first third of your talk. McCloskey?
It wasn't a paper for source of heterogeneity. That was just for the image itself. That was for but yeah, I can send some stuff around on heterogeneity. There's been a lot of different discussions of this, kind of in different fields, thinking about it. But what actually just triggered an interesting thought. Why I gave this is on first time I give it a talk on this work. It's in revision that I'm resubmitting today, and the ecologist in me kind of is how I think about the stats side of this thing, which is beyond like the binary of things work or don't work. I think if you've ever done field work or just even gone birding, right, you realize that all the forces kind of can contrive to make things go one way or the other for your day, for your data collection, for whatever else. Like ecologists live in heterogeneity. Everything is heterogeneous, right? Whether or not you get data one day, if it rains instead of if it's not, these sort of factors impact every aspect of our data collection. And it's kind of funny to me that we then expect the last step for everything to neatly divide up, right? And I think it makes, of course, things are heterogeneous. I think if any field is really aware of this, it's ecology and evolution, where everything is just really noisy, and you're lucky if you make sense of it. Like it's a very good day when you've learned something about a natural system that's evolved. It's hard.
And I should say that about the tangent thing, I think I misspoke. I should have said some people might think it's tangential, but when I say that it behooves us as scientists to know, to be informed about this history and to take it very seriously. Obviously, I personally don't really think it's a tangent. I think it's very much at the core of what being a scientist should be. So I just wanted to clarify that.
I figured that was your meaning.
But it was a really interesting thought. I know.
I figured that was your meaning. I wanted to
This
reaffirm.
This has been a really interesting talk with lots of different things coming out of it. So,
and I really appreciate the edit at the end. This is one of the things that I've been like mostly concerned with the math and the theory and that modeling part, but the question of like how this all fits into how science is done, like one of the reasons why this talk has so many more questions than answers is I don't think I should be answering all these things, right? Like I'm happy to raise the question, say if I make this different model, it looks different, what do you think? But I think answering these questions should be a thing that takes into account the history, the perspectives, the ways in which stats are used, the sociological factors that impact how we do science, who benefits, who can do science. I think all of these things kind of fit in here. And so it's really great that we got to touch back on that here towards the in the discussion. I like that, Eduardo, the atomic is great.
It is mine. It is mine. Ron should take the credit for that. But it is uncertainty. It is we have to really start embracing the fact that we just don't know as much as some of those papers seem to claim. We don't know, and that's we're for crying out loud. Isn't that why we love what we do? That we are marveled every single day. I was talking to my son Facundo. Some of you met him in Fine. He was just he's in the middle of his field season. He was telling me how some of the predators are preying on the eggs and chicks that he needs to study. So he was concerned because 2 weeks ago they were making a mess. But what he doesn't know, he said he's baffled because the raccoon goes to the nest, eats all the eggs, and then the female mom keeps bringing food for another 24 hours when there's nothing in the nest. So anyway, it's making me think of the natural history, the uncertainty, and everything what we teach. But then when it comes down to writing the discussion and conclusions, we seem to forget what we're teaching. Not to mention that we teach that evolution occurs through small changes, but then we expect our studies to find these huge changes that will give us the p-value we want with a sample size of 10. Well, it doesn't work.
I don't know if anyone here has had the pleasure of meeting Henry Horn, who's a dear mentor to me on my PhD, and Kaya as well. After I gave my second year talk, I asked him what he thought, and he said, the best thing about it was that it was very unclear. It was very clear exactly what you didn't know. And I think that that's something I try to do in my talk still, is just, I think the uncertainty thing is about just, it's much more interesting and it's much more important to say all the things you haven't learned and are wondering about than it is to make declarative statements about things that must be true.
For a long time, when I was a PhD student, I think, I used to have this quote at the end of the talk. I think it's by Henry Horn, the ornithologist, who said, I started with a list of questions. I ended up with another list of questions. With a list of questions. It's a measure of progress that the set of questions are different.
Yep. Yeah. He has a lovely book that he spent his last 30 years of his career putting together called Social Butterflies. And it just came out after his passing, tragically. But it's seriously, if you, it's filled with that kind of insight. I'm going to put a link in the chat. Oh, there's a cheap paperback too, which is great. He has a whole section on one that's just called Data Generated Narcosis, where he talks about how you collect data of some certain type, and then having once decided it was a good idea, you continue collecting that kind of data, getting excited about all the data you collected, and then after a while you realize that you were just kind of high on collecting that kind of data, and you don't actually remember why it was you were collecting anymore. That I think kind of fits this talk in general, but is a, yeah, I know, yeah, so more data.
Joe, what can you, I wish media outlets would stop, actually science reporters. It is something I've been meaning to ask some of my colleagues, some of them at Yale. Why do they keep writing this new study found? Why do we have to find in the newspaper coverage of this new study, as opposed to a science reporter is going to spend a year producing one of those very solid pieces that sometimes they do research on other topics. Say, you know what, I spent a year, now I don't get just 800 words in the New York Times, but I get a central page of 5,000 words summarizing our understanding through science of a given topic. Not a study found, but a reviewed 10 years of research. We never get that. And I don't think we're doing society a favor by reporting every single little study, given what we're discussing here.
Yeah, and this is an interesting thing, and it's something that's kind of near to some of the work I'm doing here, because I'm at the Columbia Journalism School now, although I'm a social scientist and working with journalists, and one of the things that we've talked a lot about is like, how do we improve the state of science journalism in general? Because in the pandemic, obviously there was quite a bit of science journalism that led people astray. There's also a bunch of science that led people astray. I think part of the problem is the science side, the supply side, right? If scientists are making studies saying that, chocolate cures cancer this week and chocolate doesn't the next week, journalists writing up on that is a downstream problem from the upstream problem with the kind of things science produces and the claims they make, right? So some of this is internal to science, but of course journalists have an obligation to do some fact checking and such, although it can be really hard for journalists to have the domain knowledge necessary to fully vet and fact check things. And if a scientist, especially in a reputable journal, says something, you can call it a scientist, but it can be quite hard to debunk it. And then on top of that, the pressures of in journalism now is like, it is a click-based industry for many outlets. They need to drive revenue and stuff. And so there probably are quite a few journalists and outlets that tried not to do that. And now they're gone, so there's a selection there for headlines that say scientists found this. And they actually do A/B testing on headlines to find the ones that are most effective and most engaging. And then they run those because their budgets are ad driven in a lot of outlets. And so I think it's unfortunate, but that whole ecosystem of science publication, or scientists ourselves chasing really catchy titles that get us into journals, then turns into a catchy title for a outlet that has to be catchy, otherwise it won't get shared and read in the company. So I think it's a really interesting structural incentive problem that has always been there and is exacerbated on an attention economy of the internet these days.
But I want to, I think we touched on this. I'm glad that is Theo around. I mean, Rag is around still, and Nancy's here. We had this panel of editors. Authors don't get to decide if their title gets published. It's editors and reviewers.
Yeah.
So let's not blame it on the author that the catchy title gets published, because it's somebody else who decides we're going to go with this title.
Might not be anyone at all. It might be a search engine. It might be an algorithm too. But yeah.
No. But it's the reviewer. I'm sorry?
I'm battling with my editor just today not to use the title he wants to use.
Yeah.
I also think, Eduardo, what you were saying, we should not leave it to journalists. We should be doing that. We should be spending a significant part of our research taking an area which is not the way I work in, but what I understand, and look at 10 years or 20 years of data and keep writing in the public domain. That should be what scientists should be doing. And we will do that if you don't make my promotion dependent on how many papers I publish. So we should.
I laugh because for those of you who are not familiar with Rags, I mean, please check him out. He's an outlier, right? None of us, I mean, I don't know how many of us can do the kind of science communication he's been doing over the years. And it's fantastic writing. Yes, I agree. I wish I had the motivation and the skills to do it. But Joe, go back to you're in journalism. Well, I think that if somebody's getting the degree in science reporting, at the very least, they should know that it isn't a discussion they should check, but the methods. That it isn't right. So, and sometimes I wonder what they're being told in the school of. I'm sorry for my science journalist peers, but if they choose to write their piece based on the discussion, well, they could have read the Sunday newspaper, because that is not where the science rests.
To be clear, a lot of journalism degrees are just general journalism. Some people do lean towards science journalism, but for a lot of the students here and in many places, they just get a journalism degree, and if they're inclined towards science, they might take a class or an elective in it, right? And so ultimately, if you're doing say a 1-year master's or a 2-year master's in journalism after your undergrad, or even during your undergrad, you just have an undergrad degree, you only get, maybe one stats class, one or two science classes, and the amount of time you have to devote to that domain knowledge is somewhat limited. And there are fantastic science journalists out there that really do dig into the methods and ask hard questions. But you also might just get assigned to the science beat when you're a tech reporter, right? So there's a lot of ways that you can wind up in these spaces where, and even if you have all that, it's really sometimes quite hard when you're a journalist and you have some prominent scientist. The example of this that comes to mind was not a specific example. I'm going to skip that. But in the pandemic, there were certain really prominent scientists who early on argued that there would not be a lot of deaths and that COVID wouldn't kill many people. And they had these problematic studies that others exposed statistical issues in. But before science could respond to those stats problems, newspapers ran it. And this is someone who is really trusted in the field, who is who's been known for like promoting methodological rigor, like someone who has thousands of papers. How can a journalist look at someone like that, and their team of authors at a major institution during a crisis and say, like, I'm calling bullshit here? Like, it's very hard to do that as a journalist. So of course they cover it, and no one else has said anything else yet. And they reach out for a bit of, feedback. And so this is the kind of space where I think these things get really hard, is when you have prominent journalists publishing in top outlets, things that are incorrect from major universities. There's not much a journalist can do there, unless they want to start saying like that is the fact checking. It's a little hard to, in a sense. There are strategies here that many great journalists do use, but it's hard also on a short deadline. You've got 8 hours to write a piece on this paper, and they need it by 5 p.m. and you get a quote from the author if you're lucky, and then you run it. Editor chooses the headline and it goes out there. Like, these things are hard.
Joe has dealt with quite a few journalists on his science. Joe, do you have like a list of journalists that you don't work with or like to work with based on how well they report your science?
Oh, I've actually never had anyone that was bad to work with. Every journalist that I've worked with has been great, but that's because most of the journalists that I worked with were filtered by people that ran comms for us at UW. Nice. So I only saw the good. Like in general, when I get emails from journalists, I usually just check to see if they're from a reputable outlet. I kind of read a few of their stories and see if they have an axe to grind, because sometimes people do. If that all looks good, then I'll talk to them. And I think the thing that's just most important is like, is keeping your wits about you if you're talking on the phone, especially not answering written questions, is just to think, what's the actual answer to this that I'm willing to give in this space? And that usually doesn't go too poorly. Sometimes you get some like kind of funny bad coverage of a thing where like it's not like, I haven't had any negative coverage, but I've had some like offish coverage, and then it just disappears in 3 days and no one cares about it. Once we had an extremely far right-leaning outlet cover research in Ian's lab on virtual reality and fish, and they're like, "This is cool." Like the coverage was actually just like about the science. It was like they created a virtual reality thing for. And we were like, and we're like, "Oh no!" And then we open it, we're like, "It's actually fine." So it was kind of a surprising moment.
Hey, Joe, you mentioned that if I follow you, you were suggesting that we try not to write down answers to the questions when we're approached. One of the reasons that I've stayed away from that is because more and more, this happens with the journalists as well. I feel like I'm doing more and more of their work.
Oh no, written answers are fine. If you want to be careful, writing is really, really good. But often when
but I'm being asked. I said, call me and we talk. And I said, no, I'll send you questions. I said, well, but then I'm writing the piece. Maybe a co-author if I need to answer all the questions in writing. It didn't used to be like that, because we know how it is. They just collate my responses, they tweak it here and there. Bingo, I wrote their piece. Am I missing something here?
So I mean, depends on the journalist. The ones I've been very lucky here. Sometimes they do it as a favor to be a little bit careful in crafting your answer so it doesn't get a little bit misread. And that can be nice. It depends again on how much they ask. Like if the questions are really specific, I don't mind it. If like, hey, we read your piece, we've like written all this, we understand it, how it fits into things, but here are some specific things we want kind of quotes or comments on, I think that's fine. But when it's like, tell us what the thing is about, tell us your major findings in your own words. Like, the thing is, like, I don't know. And those emails, I respond back that I don't have time, or I don't respond at all. Because it doesn't, again, like you said, sometimes they do ask you to write the whole story for them. And you're like, did you read it?
It's already 5 minutes to the hour. I don't know how it felt to you, but it really, time flew. We had a wonderful, wonderful discussion. I want to just don't rush it in thanking the YouTube community. I will thank you all for being here. At this point, I'm going to stop the live streaming. So